Ever found yourself wondering why your phone signal just vanishes inside a metal locker? Or maybe, why you're actually surprisingly safe inside your car during a thunderstorm.
Yeah, those everyday things.
Exactly. Well, today we're doing a deep dive into the invisible forces behind all that. Electric fields, specifically how they interact with conductors, materials that let electricity flow, and how that leads to this really cool concept called the Faraday cage.
It's fascinating stuff.
Great. So, okay, to really get the Faraday cage, maybe we should start with the basics. Like, how do electric charges even react when they're in an electric field?
Good starting point. So, positive charges, they naturally want to move along the electric field lines. Think of it like going downstream.
Okay, with the flow.
Right, but negative charges, like electrons, which are key in conductors, they do the opposite. They move against the field lines.
Against the flow. And does it matter how heavy the charge is?
Absolutely. Think back to Newton's second law, EFMA. The electric force makes them accelerate. But if the mass is tiny, like an electron's, the acceleration is huge.
Ah, so they can move really, really quickly in response.
Almost instantly. That speed is critical for how conductors shield things.
Right, okay. So let's take that idea, there's fast-moving electrons, and apply it. What happens if you put a whole conductor, say just a metal plate, into an external electric field?
This is where the shielding effect, the Faraday cage idea, really kicks in. As soon as that external field hits the conductor, those free electrons we just mentioned, they react immediately.
They move against the field, you said.
Exactly. They surge against the direction of the external field, piling up on one side. That makes that side negatively charged.
Which must leave the other side positively charged, right? Because the electrons moved away from there.
Precisely. You get this separation of charge across the conductor. Now, the crucial part is what this separation does.
It creates its own field.
Yes. This separation sets up a new internal electric field inside the conductor. And critically, this internal field points in the exact opposite direction to the original external field.
Ah, so they fight each other.
They do more than fight, they cancel each other out perfectly. The internal field grows just strong enough to completely nullify the external field within the conductor.
Wow. So zero net electric field inside. That's the shield.
That's the essence of the Faraday cage. The conductor rearranges its charges to prevent the external field from getting inside.
So that's why my phone doesn't work in a locker. Or, if I wrap it tightly in aluminum foil, the metal blocks the signal, which is an electric field.
Correct. Radio waves, cell signals, they're electromagnetic fields. The conductor shields the device.
And the lightning example, the car.
Same principle, just much more dramatic. The car's metal body acts as a conductor. When lightning strikes, that huge current flows around the outside of the car body.
Not through the inside where you are.
Exactly. It protects the occupants. And it's really important to remember, it's the metal cage doing the work, not the rubber tires. They offer very little protection from lightning.
Good safety tip. So if power lines fall on your car,
Stay inside. Absolutely stay inside. You're safe in the cage. Wait for professionals.
okay, that makes sense for external fields being blocked from coming in. But what if the charge starts inside the conductor? Like, imagine a hollow metal ball with a positive charge placed right in the center.
Ah, the inverse scenario. It's different, but follows the same logic of electron movement. Those free electrons in the conducting shell are attracted to the positive charge inside.
So they move inwards.
They move to the inner surface of the shell. They gather there to essentially neutralize the effect of the positive charge inside the cavity.
Okay, but if electrons move to the inner surface, what does that leave on the outer surface of the shell?
It leaves behind a net positive charge. Since electrons, which are negative, moved inwards, the outer surface now has a deficit of electrons, making it positively charged.
And that charge on the outside.
That charge on the outer surface now creates its own electric field, but this field radiates outwards, away from the conductor into the surrounding space.
So wait, an external field can't get in, but a field generated inside can effectively get out.
That's the key distinction, yes. The conductor shields its interior from the outside world, but it allows fields originating inside, or rather the effects of charges placed inside, to project outwards from its outer surface.
But the field is still zero within the actual metal itself, right?
Correct. The bulk of the conducting material remains field-free in both cases. It's all about charge redistribution on the surfaces.
That's a really elegant piece of physics. Conductors dynamically shielding from external fields, but transmitting the effects of internal charges outward.
It really is. And when you stop and think about it, well, electric fields are everywhere in modern life.
True. our devices, communication, power.
So, considering how fundamental this Faraday cage principle is, how might a deeper grasp of it shape, say, future technology? Think about securing data from electronic eavesdropping, or shielding sensitive medical equipment even better, or maybe even protecting astronauts from radiation in space.
Or even new ways to manage electromagnetic interference. Lots to think about. It makes you wonder what the next innovation based on this simple shielding principle might be.